Hi, Doug here. So it's been a few days since our last video. A lot has changed. So I was running this motor at 480 volts. I was trying to do 240 to 480 and then 483 phase through the rotary converter out to the robot. The problem was this motor is an old industrial air compressor motor, old ball door. And whenever you take a motor like this, you usually have two sets of coils for each phase, and you have them in parallel for low voltage. When you go to high voltage, they go into series like so. If one of these coils happens to be like a few wraps shorter or shorted out on the insulation internal from all the years of work, there'll be an imbalance between the three phase legs on the resistance or the generated voltage, depending on what it's operating under. The problem I was having when it was running at 480 volt, on two of the legs I get 480, and then on the generated phase I'd get around 600 volts. I tried moving capacitors, that wasn't the problem. I tried moving motor legs, and the problem moved with that motor winding. So short of rewinding the motor or finding a new motor, I had to make this work. So what I did is I switched everything back to 240 volts. I rewired the motor from series to parallel. So if you have one of these bad coils, it compensates with the coil next to it to average it out. And at the lower voltages, those deviances are only a few volts as opposed to tens of volts. So everything got dropped down to 240. At 240 volt, I had to redo my capacitance. These are 100 microfarad. I'm running them in series, so I'm getting 50 microfarad per capacitor. These are rated at 700 volts. These are film capacitors or run capacitors. So as reference to my original video, this breaker box here, this dual pole breaker takes 240 volt, 30 amp single phase, comes in through these two blue wires, goes to the two capacitor banks, wired in series. They're connected together in the center for the phase leg that's the generated phase, and that goes to the center phase of the motor here. What I've also added, I now can use start capacitors. These are about 350 microfarads at 240 volts of microfarad capacity. The reason these are so small and these are so big is because these are electrolytic and they are for short-term use. These are for long runtime, continuous use, and these are film capacitors. So what I'm doing, these capacitors are on a second breaker here. All that's doing is turning one leg of these onto this outer phase leg, and then they're connected to the generated phase leg. So it's only between L1 and the center phase leg. So when I started, I'm going to hit both breakers, which turns the start and run capacitors on to get it running. The second it gets up to speed, I turn this second breaker off, which disconnects the one leg from these start capacitors, which basically puts it into a fully operational three-phase generator. At that point, the motor should be running and we can move on. So let's get the motor up and running first. And you should notice it runs a lot quieter now because everything is well balanced and only a few amps. I forgot to talk about the elephant in the room here. This is a clamp-on current meter. It measures 0 to 75 amps AC. The breaker is set for 30 amps, so we're going to try to stay below that. Watch it. You may see a jump during start because these start capacitors pull a lot of current, which is why you can't leave them run for very long. So I'm going to go ahead and fire both breakers up and then turn the second one off, and you should hear the motor start, and you'll actually watch it start too. 3, 2, 1. You saw the jump in the breaker. The motor's now running. It is so much quieter now. I keep wanting to yell over it, but I don't need to. So we're now generating 240 volt, three-phase, well-balanced within 5% coming out of this system. You'll see these three wires. Those run down. We're going to move ahead down here. Down here, the three-phase legs come down at 240 volts, and I have these T transformers wired in open delta auto transformer boost mode. I'll draw a schematic and put it up. Basically what they're doing is taking the 240 volt three-phase and converting it to 480 volt three-phase. And open delta means when you have a triangle with three phase legs, one of the coils is missing. It's open delta. Delta means triangle. So I only have two transformers. So it still generates three phase. It induces this third triangle. But the problem with that is you get something called a wild leg or a hot leg on that one. So if I were to measure between any phase and ground, it'd be about 240 volts. But between the wild leg and ground, I get about 370. So for single phase operation, pulling to ground with a neutral, not ideal. But because I'm using fully three-phase, no neutral, this seems to work. I do note I have to derate these capacity of these transformers by about 56% because of that open delta configuration. Also, the robot has a three-phase rectifier, so it's pulling equally across all three legs, so I don't have to worry about the imbalance that awfully comes with the soft leg of an open delta. So I talked enough. Let's see our voltages. So this is our one phase here, the green. Our second phase is the white. We have 258 on one phase. And then on this one, 246. And if I measure across the two solid phase legs, we have 246, 45. So that's good. Now let's check our output phases. So I'm going to go to white to green here. And we have 405 volts. And then I'm going to go from phase to phase here. 388, 390, 389. And then I'm going to go to this phase leg. and we're about 397. So very, very close. The robot can run between 380 volts and 500 volts. If I went to the 0 tap here, which I'll just show you here, that voltage jumps over 500 volts, 518, which is a little bit above the limit of the robot. So that's why I'm dropping to this lower tap here to give me my 340 volts, if you will, 400. So that is why it then leads there. It comes across over to the robot controller, and I now have this phase connector here. So what we're going to do is, for the first time ever, you're going to follow along with me, we're going to fire up the controller and see what happens. So I'm going to go ahead and turn it on. Actually, I need to close it first to turn it on. So there we go. We're going to look for any jumps in current on our meter here. This robot, I remember from when it was installed at the factory, was terrifyingly long it takes for it to boot up. It'll sit there for a while and make sure the phase legs are all happy before it actually boots. There we go. And we just got a pulse on the meter. It was brief. It was about 5 amps. I heard the fans kick on the controller. So that means it's happy. Now we wait, and we're going to look at the controller here, and we're going to see if it boots up. I'm going to have you guys look at that. Oh, look at that. So it's currently booting. I'm going to check the voltages on the transformer. You keep an eye on that for me. I'm going to read off the voltages here. So phase 1, 400 volts. Phase 2, 383. And phase 3, 395 volts. So I'm going to pull this out so you can see it better. It's actually loading, which is exciting. Startup in progress. For 9 seconds. And again, this is such a long process it goes through. Now, the e-stops are all disconnected, so it may not let me actually run the robot here. So we're going to see. I'm going to hit reset. Yeah, external e-stop press. So it won't let me run it at the moment. But I'm not getting any alarms outside of the emergency. Yeah, just an emergency stop. So it thinks the power is happy and viable. So make sure you stay tuned. Next video, we're going to see if the robot actually runs. And this is fantastic. We are now generating 480 volt 3-phase from 240 single phase, and we're able to power up an industrial robot here in the lab. Exciting stuff. Make sure you stay subscribed and watch along for future updates. Thanks for watching.